Welcome to today's webinar, Liftoff with Precision, Converge application in drone simulation, brought to you by Convergent Science. Thank you for joining us today for this new installment of our webinar series. My name is Matthias Sulis, and I am part of the business development team at Convergent Science. I will be your host for today's event. I am glad I can be here today and learn how Converge CFD software can be used to model drone propellers, as well as full body motion with maneuvering control, and how CFD can help you extend the usage of drone. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flow in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speaker for today's event, Shengbai Shi. Shengbai is a principal research engineer at Convergent Science. He obtained a master's degree in mechanical engineering from Johns Hopkins University in 2012 and his PhD in ocean engineering from the University of Delaware in 2016. His PhD thesis focuses on large eddy simulation of wind turbine under various atmospheric thermal conditions. Since joining Convergent Science in 2016, Shengbai has worked on development, validation, and support for wind energy and other renewable energy projects. Without any further delay, I will now pass the ball to Shengbai. Thank you all.
Thank you very much. Thank you, Natia, and thank you for joining the webinar for this drone simulation in Converge. So as we can see, the drone plays a more and more important role in our daily lives. We can almost see it everywhere. Not to mention that it actually serves a lot of very important roles in the civil services. Today, I'm going to only talk about the civil services, not mentioning the military applications, but they share some very similar features. For example, the drones can be used to do a lot of work, such as search and rescue the civilians and monitoring. It can be used for the inspections of the infrastructures. It can be used for the disaster responses as the wildfire fightings, and it can be used for the agriculture, for the mapping and surveying, and it has been proposed to be used for the delivery of your goods, of your online purchased products, and also it has already been widely used in entertainment for taking the pictures, for taking the videos, and you can see all those kind of videos on YouTube and somewhere online. And because of the fast development of the applications of the drones, we need a better design of the drones to make that more aerodynamically economic, to make them the battery life optimized, and make them the operations more stable and reduces the noises. And for all those purposes, the computational fluid dynamics CFD can play a very important role, because the CFD provides you the detailed, very accurate physics. Also, it's a relatively inexpensive method for your studies, for your design work. And then why Converge CFD among all those candidates? Because Converge CFD has a lot of very interesting or favorable features that makes it especially suitable for this type of the problems. For example, Converge CFD has the autonomous meshing with adaptive mesh refinement, which allows you to simulate the rotating blades in a relatively easy way, as well as capturing the wake structures in great details without too much manual interference as in the case setup process, because all those meshes are generated automatically during the simulation. And also, if you want some additional refinement near the blades, you can also we also provide the innate boundary layer mesh at the blades, which you can be used together with the Cartesian mesh for your simulation. And in order to increase the numerical efficiencies of this type of simulations, we provide different solutions that can be used together. For example, we have the multiple reference frame approach, which allows you to simulate the rotating blades in a stationary way. And we also have the rotor models, which totally eliminate the geometry of the blades, meanwhile give you the correct aerodynamic forces of the blades to your simulation. And if you are interested in study the dynamics of the whole system, the whole drone body, then we can provide the fluid structure interaction modeling capability for your projects. And we have a rich library of turbulence models that you can choose to use. We can do the ROES, RANS, even DES, and even DNS if you preferred. And if you're interested in the study of the noise levels of the drone or of the propellers, and we have multiple aeroacoustic models that you can choose from. And besides those, we provide a lot of other physical models, such as combustion models, such as spray models, which allows you to expand the applications of the drones. And let's start from the simulations of the propellers, because that is the most difficult part or the most challenging part of the drone simulation from my point of view. The blades basically it provides the lift force of the thrust force of the drone, and it's the most sensitive part to generate to the aerodynamics, and therefore you need some special attention to the mesh refinement near the blade. And there are different ways of simulating the aerodynamics of the propeller blades. The most conventional way is the blade resolved method. Basically, this method uses the CFD cells to resolve the geometry of the blades. In Converge CFD, we provide different types of the meshes that helps you to resolve the geometry. By default, we are using the Cartesian mesh to the cut cell based Cartesian mesh to resolve the geometry, and this mesh is automatically generated during the simulation. And as I said, you can add the adaptive mesh refinement to do the mesh refinement during the simulation at the locations where the flow phenomenon becomes more important. And also we can provide the body fitted mesh to be added on the blade, and that body fitted mesh is inlaid together with into the Cartesian mesh to provide you better resolution near the blade, near the geometry. And here is a very typical example of using the combination of the body fitted mesh and the Cartesian mesh for your simulation. And as you can see, the body fitted mesh has a very fine resolution, especially in the normal direction of the blade. And this body fitted mesh only occupies a small layer near the blade, and away from this layer, then we are using the Cartesian mesh for the rest of the domain. And both the Cartesian mesh and the body fitted inlet mesh are able to move together with our geometry automatically. And if you implement this the blade resolved approach correctly, then this method can give you the most accurate results. It captures most of the flow details, and it relies less on the numerical models. So this is the most accurate way. But in a lot of cases, this type of simulation can be quite expensive in the computation. And in order to accelerates the numerical efficiency of this type of blade resolved simulations, we provide several approaches. One of them is using the multiple reference frame approach, which solves the transport equation in the rotating reference frame, so the mesh and the geometry, in this case blades, are fixed. So this method basically allows you to use much larger time step to deal with the rotating blades, and it uses one reference frame near the blades and uses another away from the blade. So for the near the blade, we're using the rotating reference frame, and away from the blades, we're using the stationary reference frame, which gives its name the multiple reference frame method. And another approach that is helpful to increase the numerical efficiency is to use the variable mesh size and the time step control. Thanks to the powerful meshing algorithm in Converge CFD, we are able to use different resolutions at different stages of the simulation. Because in most of the blade simulations, the flow can be regarded as either a steady state or the quasi-steady state. So therefore, which means we can use some relatively coarse mesh to wash out the initial conditions and to build up the flow field in a relatively quick way. Then we can, once the flow field is relatively, it's more or less established, then we try to refine the mesh based on that and gradually increase the resolution. Eventually, at the very last stage, which occupies, let's say, 10% of 5% of the total duration, we use the finest mesh for that final stage. In this case, we activated the inlet mesh with the finest resolution only at the last stage of the simulation. So by using this approach, we can save more than 90% of the runtime for this type of simulation compared with the constant mesh throughout the whole duration. And next, I'm going to show you a validation case that we performed for the blade resolved simulations. Here we are using the Cartesian mesh to simulate this pressure sensitive paint blade, PSP blade, which is part of the AIWA rotor hover validation program. And you can find the detailed characteristics or properties of the blade from this reference paper. So I will not repeat all those the numbers here. And in terms of the case setup, as you can see, we only simulate one blade instead of the whole propeller. And we're looking at the RPM equal to more than 1,000. And we are using the K omega SSD model as a turbulence model. And we are looking at 3 different pitch angles at 4 degrees, 8 degrees, and 12 degrees. And in this simulation, as I said, we are going only use the Cartesian mesh without the innate body fitted mesh. And the finest resolution here gives us a Y plus ranges from 1 to 400 at the blade at different locations. So in terms of the results, we are going to look at the thrust coefficient, the torque coefficient, and the figure of merits. And we compare our simulation results with the data from the literature. And here, what I'm showing are the results from our simulations. And the right lower figure showing you the comparisons between the CT and CQ figure and the CT versus FM figure from our simulations versus the reference, the CFD simulations from the reference paper. And as you can see, we are simulating 2 solvers for the same problem. We are using the transient solver as well as the steady state solver. And because we are comparing CFD model versus CFD model, so we do not expect a 100 exact match between our results and the reference data, but instead we want to show that our simulation gives the similar trend in line with the reference data and also between the different solvers. As you can see, our transient solver and the steady state solver generates the correct trends at the 3 different pitch angles. And you may notice that the transient solver seems to be more close to the reference data, whereas the steady state result is a little bit away from the reference. But as I said, this is not a apple to apple comparison. But in terms of the computational cost, this simulation, even for the single blade, in order to have a good resolution, it requires about 32 million cell count. So it's a relatively heavy simulation. In terms of the CPU hours, the steady state is only uses about 1/4 of the runtime compared to the transient solver. So like in many applications, we have to make the trade-off between the numerical accuracy and the numerical efficiency. And in order to further boost the numerical efficiency, we introduced this blade modeled approach. Unlike the blade resolved approach, the blade modeled approach actually get rid of the geometry of the blade. Instead of resolving the geometry of the blade, it uses some method to calculate the aerodynamic effects of the blade and add those aerodynamic effects as a body force in the Navier-Stokes solver, and therefore the fluid solver feels the effects from the blades. There are different types of the blade model, the blade modeled approach that you can choose from. In Converge CFD, we introduce the disc model, actual line model, and some other type of the rotor models. And here we are going to focus on the actual line model in this presentation. The actual line model was originally developed in the wind energy industry. It was used to simulate the blades of the wind turbines, and we transplant this method into the simulations of the drum blades, and it turned out to give us some very satisfactory results. And in general, this method, instead of resolve the geometry, simplifies each blade as an actuated line, which can be further divided into multiple airfoil points. And at each airfoil points, we calculate the angle of attack, and then we find out the lift and the drag forces from the turbulated data. And once we obtain the aerodynamic forces at each point, we use some analytic function to distribute or to project the forces from the actuated lines to the surrounding CFD cells, such that the flow field can feel the existence of the blade. And at every time step, we rotate the angles of each actuated lines to generate the rotation effects of the rotor. And by using this method, as I said, because it does not resolve the blade, it allows a much coarser resolution and a much larger time step, which significantly saves you the computational cost. We found that this method can run 10 times, even to 100 times faster than the blade resolved method. And another advantage of using this method is that it actually parameterizes all those blade properties, such as the chord length, such as the pitch angles, the twist angles, airfoil type, everything is parameterized. You just need to simply change the parameters to change the blade characteristics there without touching the mesh, without touching the geometry. So this method allows you to have a very fast turnover time for your design process, and especially good for the optimization studies. And again, as I said, this method is two-way coupled with the CFD. And here is an example showing the validation of using the actual line model for this particular propeller. This is a single 16 by 4 inch propeller. You can find the details of the propeller in this reference paper. And here we are using a pretty coarse mesh for the propeller using the actuated line model, and we are using the K epsilon RNG range model as a turbulence modeling, and we are looking at 4 different RPMs from 1000 to 4000. And on the right figure shows the comparisons between our actuated lines CFD simulations compared with experimental measurements, as well as the blade resolved CFD data from the reference paper. So as you can see, this is the thrust force on the rotor, and this is the torque from the rotor. As you can see, in both the quantities, we have a very good match to the reference data. And the right lower figure showing you the comparisons between the blade resolved CFD and the Converge actuated line model CFD for the velocity contours in the wake region. As you can see, we have a good match between the two CFDs. And with those being said, let's take a look at how to use Converge CFD to do some serious studies. Here, what we're looking at is the study of the ground effect of a DJI propeller. And the ground effect is when you have a rotor or a drum operating near the ground, because of the interactions between the wake from the rotor, from the propeller and the ground, you are going to have some additional lift force on your drum. Therefore, the aerodynamics is different than what you expected, and as well as the control logic should be adjusted to include the ground effect. And in this case, we are looking at this DJI Phantom 3 propeller, which has 2 blades and has a blade length about 0.12 meter. And in this particular case, the RPM is relatively high, close to 10,000. And we are simulating, we are using 3 different, we're simulating the propeller by using both the blade resolved method and the actuator line method. For the blade resolved method, we are looking at different types of the meshes. One is with the Cartesian mesh only, with a resolution equal to 0.3 millimeter at the blades. That gives us a Y plus around 20. And we also have the inlaid boundary layer mesh together with the Cartesian mesh for the blade resolved simulation, with the finest resolution around 8.2 micrometer at the blades, which gives us a Y plus around 2. And in both of those blade resolved simulations, we are using the MRF approach to accelerate the simulation. Here shows the case setup for the blade resolved cases. As you can see, near the rotor, we generate this additional region to consist of this MRF region. Inside this cylinder, the coordinate system is the transport equation are simulated in the rotating reference frame, and outside of this cylinder, the transport equations are solved in the stationary frame reference frame. And for the actual line model, the resolution is much closer compared to the blade resolved cases, and it uses the transient solver. Now let's take a look at the results. The first thing I want to show you is the mechanism of the ground effect. Here, what I'm showing is the velocity contours from different heights by using the Cartesian blade resolved case. So the upper one is with the h over r equal to 6. H is the height, r is the radius of the rotor. This one, as you can see, is very close to the ground. As a result, the wake has been deviated from the center of the rotor to the sides. Therefore, it causes a relatively low velocity region compared to the case without the ground effect. So because of this low velocity region, it has some higher pressure on the lower surface of the blade, as showing in this figure, where I show the pressure distribution on the upper surface and the lower surface on the propeller. And the right upper figure are the results indicating the ground effect at different heights in terms of the thrust force at different heights. And as you can see, different symbols represents the different CFD simulations, as well as the results from the empirical models. As you can see, no matter which blade or approach we adopt here, all our results seems to capturing the ground effect in a very satisfactory agreement with the empirical data. Basically, when we have a distance very close to the ground, we have an increase of the thrust more than 10%, around 15%, and then that thrust gradually to decrease until it goes back to the level where the ground effect is minimal. And the lower right figure shows you the comparison between the actuator line CFD and the blade resolved CFD with the inlet mesh in terms of the velocity magnitude in the wake region. And as you can see that despite of the different rotor approaches, we can capturing the very similar velocity patterns in the wake. And now let's shift the gear a little bit from the aerodynamics to the aeroacoustics, because the noise is a very important factor in the applications of drones, especially in the urban areas, and the people are quite concerned about the noises from the propellers, and therefore it's very important to first of all have a good assessment of the noise levels of the propellers of the drone, and then have some de-noise designs to make the noise reduced. And then and actually Converge can provide you some very handy and reliable aeroacoustic models for this purpose. For example, if you want to identify the noise sources, you can use a near-field acoustic models such as the Proudman model and the Curly model. And if you want to predict the noise levels at some given locations, then you can use the far-field acoustic models such as FWH models, and all those models are available in Converge. And here is an example of the aeroacoustic analysis of the same DJI propeller that I used for the ground effect study. And here I look at a case where the ground effect is not included, so the propeller is far away from the ground. But we turn on the far-field aeroacoustic model to see how what kind of noise level this propeller can generate. And the first data we are showing here, the first result we are showing here is the distribution of the light hill stress magnitude. The light stress tensor is an indication of the strength of the noise levels. So basically, the larger values means it is more close to the source of the noise. And as you can see in this case, the source of the noise majorly comes from the blade, and especially near the tip of the blade. And also we have 12 different receivers evenly distributed around the propeller, which is at the center, with a radius of 4 meters apart from the propeller. And we record the noise levels at all those monitor receivers. From this study, we found out this propeller can generate the pressure level close to 70 decibel at those receivers 4 meters away. So it's quite a noisy machine from this point of view. And we found that this noise level is in line very well with what we found in this reference paper. And after this, describing the simulations of the single propeller, now let's look at how you can use Converge to simulate the whole drone dynamics. And here I use a quadcopter as an example to demonstrate how the drone dynamics corresponds to the control of the RPM of the rotors. Basically, in the modern drones, the position control is through the varying through the variation of the RPM at the respective rotors, as demonstrated in this figure. By using different combinations of the RPM, you have the different types of the motions. And in Converge, you can do this simulation in a very simple way, without too much additional effort from what I showed earlier. And Converge can use the fluid structure interaction modeling to include the aerodynamic forces from rotors and control the motions of the drone body according to the forces. And here is an example showing you the different modes of the motions by some Converge simulations. Here the rotors are simulated by using the actual line model, and the actual line model is coupled in this case with the FSI modeling of the drone body. And as you can see, we have the different types of the rotor RPM controls, and this is for the lifting process, for the yawing process, and for the forwarding process. And the red color here indicates the RPM is larger, and the green color means the RPM is lower, and the arrow indicates the rotational directions. So as you can see that by including the line model, this type of simulation can be very efficient, and you can have the combination of all those rotor controls in one simulation to have the different modes in one run. And in particular, I want to emphasize that in the forward simulation animation, I also show the mesh here. As you can see, we have some final mesh around the geometry, around the drone, and this embedding actually moves together with drone during the simulation, and this gives you a very good capturing of the flow phenomena near the drone, and meanwhile it saves you a lot of computational time. And then I want to discuss how you can use Converge for the applications of the drones. And you have to use drone for some purpose. For example, you can use a drone for the agriculture purpose, or you can use drone for the firefighting in this case that I'm going to show here. So because of the climate change, though, we are going to experience more and more wildfires, and I believe you read all those news from all kind of medias, and it becomes a big issue for our world. And drone turned out can have some very good advantages over the conventional method for the firefighting, especially for the wildfires, because it can access to a lot of locations that the conventional method are very hard to do, and it's very nimble, it's very swift to be operated, and so it has a very good potential for the firefighting of the wildfires. And the animation here shows you an example of the sprays, like for example, the waters injected from a drum that has been simulated by where the propeller are simulated by using the actual line model. And next, I'm going to show you a very specific example of this firefighting simulation. So here, what I'm simulating is a diesel pool fire where we are using the detailed chemistry SAGE model to simulate the combustion of the fire. We are using the inhibition mechanism with 42 species and 168 reactions to simulate the combustion. And for the drum, as I said, we are going to use the actual line model for the rotor to make this simulation numerically efficient. And we are going to prescribe the motion of the drum instead of using the FSI for the purpose of simplicity. For sure, you can use the FSI by controlling the RPM, but here I just prescribe the motion to make this case a little bit simpler. And then we're going to, once the drum goes above the fire, then I'm going to inject some water from the drum, and the waters are going to be simulated in the Lagrange model as the spray parcels. And then the interactions between the spray parcels and the flame of the fire will be simulated, and you will see the distinguishing process of the fire. And also, and in this case, we use AMR and embedding to improve the greater resolution for the combustion, rotor modeling, and the wake region. And here shows the animation of the process of this simulation. As you can see, the drum starts from here and goes above to the fire, where the fire is identified by the ISO surface of the high temperature. And as you can see, after some time, the water droplets has been injected from the drum, which will interact with the fire front. And at the beginning of this process, because of the interactions of the rotor wakes and the flame, the fume air mixing is enhanced. Therefore, the combustion actually becomes stronger. But once after some time, once the water liquids contact with the front as well as the evaporation of those parcels in the pool file, then you can see that the heat release rate starts to decrease. Eventually, it goes to 0, indicating the extinguishing of the flame. Okay, eventually, finally, I will make the summary here. Converge can help achieve better designs for the modern drone systems. And particularly, Converge offers a number of advantages for the drone simulations. For example, it has the flexible meshing techniques, which helps you to accurately capture the aerodynamic forces in a very easy way. And we also have the advanced rotor models, which significantly improve the numerical efficiency, meanwhile maintaining the accuracy of the aerodynamic effects. And this method also parameterizes the blade properties, which shortens the design turn over time. And Converge also provides you the FSI modeling capability, which allows you to simulate the 60-degree of freedom motion of the drone body. And if you are interested in the noise study, then we have the aeroacoustic models, and you can use a wide range of the physical models to study different applications of your drone. And here shows you the taking off process of a drone simulation. By using Converge here, we resolve the blades, and we are going to show a demonstration case simulating the same problem after this presentation. Here I'm going to demonstrate how you can set up a drone simulation in Converge Studio. And the particular problem we're looking at is a taking off process of a drone. So in order to set up the case, first of all, you have to open your Converge Studio. In this case, we are using Studio 3.1. And then you open a blank page here. Because I have already set up the case to save the time here, so I just need to import the case setup. So I just go here, import case setup, and choose a directory. And here is where I save all those input files. I just choose that, and it brings up the case setup for me in the window. In case you don't have already set up the input files, what you can do is, as you can see, because this case is relatively simple, what you need is a rectangular box to enclose the your drone. So you should have a STL file of your drone. You can load that into Studio, then generate the outer box. And let me hide the embedding here first. I will show the embedding later. So as you can see, the computational domain is rectangular box. To create that, you go to the create, then go to shape and select box. And by giving the center and the dimension in the XYZ direction, you can generate the exact looking box as what I show here. And after that, you have to flag the geometry by different boundaries. The boundary means that you are going to specify the boundary conditions on that part of the geometry, and depending on the different boundary conditions, you should divide your geometry into different boundaries. And in this case, the outer boundary will have one boundary on the side and on the top, which is going to be the outflow boundary. So it's going to be outflow by giving the initially pressure. And the bottom wall is a different boundary, and it's the wall boundary with the stationary fixed motion. So, and we are going to use the law of the wall at the ground boundary. So you can hide those boundary to expose the geometry of the drone. So for the drone, in this case, we divide the drone into 5 different boundaries, and 4 of them are for the 4 propellers, and the rest is for the drone body. And for example, the propeller 1, which is this brown propeller, as you can see, we set the boundary type as wall, which means a solid boundary, and the motion type is rotating with the movement as moving. And then we can give the rotation rate in terms of degree per second. And if you don't want to use the constant RPM or constant rotational speed, you can choose to use the file. And in this file, you can select as the either cyclic or the sequential type of the profile. And then you can use the variable RPM as a function of time. So in this way, you can have a very precise control of the RPM for each propeller. So this is for propeller 1, and for propeller 2, which has the same RPM in this case, but with the opposite rotation direction. As you can see here, this is a rotational axis. So the rotational 3 should have the same RPM as well as the rotational direction as rotation 1, and the rotation 4 should have the same as the rotation 2. So all those, each individual propeller, you can have the different profiles and you can have the different RPM. Therefore, you can have a very good control of the dynamic motion, the 60-degree of freedom motion of the drum body. And in terms of the drum body, we use the wall boundary here as well, but the motion type this time becomes FSI, means the motion of the drum body is controlled by the FSI modeling. And since we are going to use FSI modeling for this taking off process, then you can turn on the fluid structure interaction modeling under the physical models. Select that here. Then in the setup of the FSI modeling, as you can see, we define a FSI object here, which consists of all those boundaries of the drum body, of the drum, which includes the body, the drum body also, as well as the 4 propellers. And in terms of parameters, you can choose the start time of the FSI modeling, and then you can give the initial center of the gravity, or center of the mass, the location of the center of the mass here, and you can give the total mass of the drum, including both the propeller and the drum body here. And if you know the momentum of the inertia, then you can use the prescribed value for this momentum of inertia tensor, or otherwise you can ask the solver to calculate the tensor for you based on the given parameters here. Then let's take a look at the mesh control. We are using some very coarse mesh as a demonstration here. So we are using 0.4 meter as the base grade mesh. If you can show how the base grade mesh look like by clicking this grade preview. So as you can see, the base grade mesh is very coarse, which is far away from resolving the geometry here. Therefore, we need some embeddings, which means we need a local mesh refinement. So we turn on the fixed embedding, and as you can see, if we can turn on the embedding, we have some volume embedding, which has this box volume for the outer wake region or along the passageway of this lifting process, with the scale equal to 2. The scale means that is base grade divided by 2 to power of the scale. So 2 means 2 to power 4. 2 to power 2. And closer to the drum, we have a finer embedding in the shape of this cylinder, which has a scale equal to 3, which means the base grade divided by 8. And besides those volume embedding, we also have some refinement attached to the boundary. For example, at the drum body, we have the scale equal to 4, which means very much finer embedding compared to the volume embedding attached to the drum body. And we also have the embedding equal to scale 6 on the 4 propellers. And besides the fixed embedding, we also activate the adaptive mesh refinement to generate the mesh refinement dynamically, automatically during the simulation. Here we are going to use the velocity as the indicator of the AMR, and we are going to choose the SGS value as the embedding criterion. The SGS value basically is the curvature of the selected variable, in this case velocity. So as long as the curvature at one cell is larger than the threshold you specified here, then we are going to add some additional mesh refinement. All right, so and this is how we control the mesh. And this case is going to be simulated as a DES, which means we are going to use a RANS near the solid walls, and we're going to use areas away from the solid walls. So in the turbulence model setup, you can choose the DES, and we have the DDS and IDDS. Here we choose the DES based on the K omega SSD RANS model that will be activated near the wall. Okay, and also in this case we added we include the gravitational force, and besides those key parameters, there are CFL, the time step controls under the simulation time parameters, and also the solver setups under the solver parameters. I will not go to the details of those setups in this demonstration, but if you're interested, you're welcome to attend our training courses. We'll have very detailed explanation of all those setups in our training courses. And okay, now we have set up the model here, then we can export the seted model to the working directory. As you can see, there's one arrow. Once you have an arrow, you have this arrow message, because we choose to use the file but didn't give the file name here, so that's why it gave me this arrow. I just for this particular case, I do not want to use a variable RPM, so I just use constant RPM. So I just use the constant without checking this use file. And now all the case setup has been corrected. We can export the case setup to the working directory, and you choose the working directory and select OK, and those files will be generated. Once those files are inside the working directory, you can run Converge. You can run in your cluster, in your own desktop, or using command lines, or like what I'm using, the embedded run Converge command inside the studio to run the case. You can click that and select the working directory, and this is how the log file would look like. Because we are using some very coarse mesh in this case, you can see the simulation progresses in a very fast way, so we can force terminate the simulation because it will take some time to finish the simulation. To save you time, I've already run the case, and it have generated all those necessary data here. In terms of the output files, for example, you can check what is the displacement of the FSI motion. To do that, you can choose, once you have run the case, you will generate this output's original directory. Inside that, choose under the string 0 directory, you can choose all those output files to review your results. In this case, we are going to look at the FSI object.out. You choose this working directory inside this line plotting section, then you can select that file. So as you can see, after 0.5 seconds, the drone has lifted about 2 meters high. And also you can visualize the 3D flow field by loading the post file into TechPlot or to whatever CFD visualization tool you prefer to use. And I have already made some layout files, so let me quickly show that. You can load this layout file that I generated earlier. So as you can see, what I show here is a slide playing across some rotor parts, the center of the 2 rotors, and the colors are the velocity magnitudes. It will have some large velocity near the blade and a relatively low velocity in the wake region, but you can see the wake quite clearly. And in this case, we're using some coarse mesh, so you can see that actually we have some very large cell size away from the geometry and some fine mesh near the blade. And definitely this is not sufficient to resolve any important fluid dynamics, and in your real problems you want to have much finer resolution than this. And I've already generated some animations from the poster files using TechPlot, and this is how this simulation will eventually give you. And as you can see, we generate the mesh refinement automatically following the motion of the blade in the wake region as well as near the rotor regions. And thank you very much. And I will stop introducing the example case here. And thank you very much. I will stop the presentation here.